Okay, everyone, sorry about that. So today we're going to talk about digital building blocks, which are digital circuits that are commonly used in microarchitectures. I have a couple reminders for you. We've got quiz 6 I just posted today, and I'll give you until December 2nd, last day of classes, to take that because of the Thanksgiving break. So you have almost 2 weeks. The final exam is going to be on Dropbox, and you could take it any time between December 5th and 9th, and you'll have 120 minutes, one attempt, much like the midterm. And that will cover all the material that we covered over the semester. So RISC-V, ISA, System Verilog, Pipeline Microarchitecture, Sequential Logic, Timing Analysis, Digital Building Blocks, and I'll probably get to cover some material on CMOS logic in the next lecture on Monday, next week. And then Lab 4, make sure you submit and demo by December 2nd. Okay, so the first thing I want to talk about is integer addition or adders. Hopefully you guys covered the full adder in 2.11. A full adder is a 1-bit adder. It takes two 1-bit input operands, A and B, as well as a carry-in bit. The carry-in bit is like a third input. So basically you're adding 3 single-bit inputs. So the sum of 3 1-bit inputs can be a value between 0 and 3. So there's 2 outputs, sum and carry out. So carry out is, so you can think of carry out as the most significant bit of the sum, and S is the least significant bit of the sum. Does that make sense? You guys covered that in 2.11, right? Okay, so that's a 1-bit adder. Then if you make a multi-bit adder, you could think of it like a grade school type addition where you arrange the bits in columns. So you have each of the bits of the 2 multi-bit inputs are lined up in columns, and then you add the values in each column, but you can also have a carry in from the previous column, and you may get a carry out that will carry out into the next column to the left. So when I say previous, I mean the right or less significant column, right? And then you can carry out to the left column. Make sense? Everyone with me? Okay, so that's the challenge with an adder, is that you've got these carry-ins and carry-outs that you have to deal with. So there's 3 types of adders that are common. There's the ripple carry, lookahead, and prefix adder. And each of these is a trade-off between speed and resources, area, right? So the ripple carry is the smallest, most compact, but it's the slowest. The prefix adder is the largest one in terms of number of gates, but it's also the fastest. So there's a space and time trade-off with these 3 types of adders. So a ripple carry adder is where you just take full adders, single bit adders, and you just chain them together, where the carry out of each adder is connected to the carry in of the next adder in terms of significance, right? So you end up with each of the bits of the operands get fed into the full adders, each of the pairs of corresponding bits, right? So bit 0 A and bit 0 of B get fed into the first adder, then bit 1 of A and bit 1 of B get fed into the second adder, and then the carry out of the rightmost adder is connected to the carry in of the second to rightmost adder, right, and so on. So you create this chain. So the ripple carry adder is kind of a 1-to-1 match to the grade school addition you do, where you arrange the digits into columns and you add with carries, right? The carry lookahead adder, the ripple carry adder rather, this is the ripple carry adder, it kind of matches that. It's just the hardware form of that, right? The problem with the ripple carry adder is it's slow because its propagation delay in terms of when you get the slowest output relative to when the inputs change is going to be n times the propagation delay of a full adder. And so what that's referring to, by the way, is the last carry out. So the last carry out, the carry out from, in this case, column 31, which is the most significant bit, that carry out is going to be the end of the critical path. That's going to be the critical path delay for this circuit. So the time it takes, the propagation delay, the time it takes to get all the outputs to stabilize is going to be n, where n is the number of bits, times the propagation delay of the full adder, which again, the full adder is just the single bit adder, this guy. Right? Now what is what's the propagation delay of this? It's basically 2 gate delays, because if you look at the carry out, there's a AND gate that's used to compute these terms, these 3 terms, these 3 product terms, and then there's an OR gate, a 3-input OR gate that the output of those AND gates go into, right, to produce the carry out. And then the sum is a 3-input XOR gate. I think generally you're going to have the carry out's going to be the critical path of the full adder. But if you look at the whole adder architecture, the delay is going to be, the critical path delay is n times the propagation delay of a full adder, because you got to go through all 32 full adders to have the result of the add. Make sense? So that's slow, and obviously it gets slower as you add more bits to the adder. How many bits are in the adder, the typical CPU? Well, in our CPU there's 32. We have a 32-bit add. Most CPUs these days are 64-bit architecture, so they will have a 64-bit adder, more than likely, right? Okay, so if we want a faster adder, we can go to the carry lookahead adder. The carry lookahead adder is where you try to speed up the calculation of the carry-ins. So instead of having a critical path that generates all the carry-ins in order, you have some logic in there that will generate the carry-ins faster. How do you do that? You have this, you build your full adder. So let's go back. This part can be a little weird. So you have your full adder here. Normally your full adder has the carry out and the sum outputs. There's 2 outputs. But you can add 2 additional outputs to this truth table called propagate and generate. And what those mean is, if that full adder generates a carry based solely on its inputs A and B, without worrying about carry-in, right? So this guy, if A and B add up to a value of 2 by themselves, right, just A and B, without carry-in, if I have 1 and 1 for A and B, then I'm looking at, this row and that row. There's only 2 rows. Yeah, there's only 2 rows there, right, where A and B are both 1. But in both of those rows, I have a carry out, right? In other words, if A and B are 1, then I can consider the carry in as a don't care, because I know if A and B are 1, there's going to be a carry out, right? So that means that I'm going to generate, if A and B are 1, I'm going to generate a carry out regardless of its carry in. So that's what the generate is. Generate just means, yeah, there's going to be a carry out. Don't even worry. Like carry-in's a don't care because I know I'm going to get a carry out just because of the A and B inputs, right? Then there's another output called propagate. And the propagate is whenever A or B is 1, because in those rows, like if A or B is 1, the carry out will be whatever the carry in was, right? So let's look at this second row. A and B is 1, A is 0, B is 1. The carry in is the same as the carry out. In this case, A is 1, B is 0. The carry in and carry out are the same. In this case, I generated, so I'm going to generate in that case. Over here, A and B are 0 and 1. Carry in is 1, so therefore carry out is 1. In this row, A is 1, B is 0. Carry in is 1, carry out is 1. And then the last case is a generate case, right? So propagate means if A or B is 1, I'm going to propagate the carry in. Whatever the carry in is going to go to the carry out, right? Yes?
Could we more easily define that as AX or B propagate? Or
AX or B?
is it propagate?
Oh, X or. Yeah, you could. I think so. That's usually it's or, just A or B.
Because there's overlap.
Yeah, there is an overlap. If they're both 1, then it breaks or if they're both 1, then it breaks the rule, because if they're both 1 here, the carry in is 0 and yet the carry out is 1. But generally the way it's set up is it's A or B, because if the generate is 1, then that'll give you a carry out, right? So the way it's set up is if the way that
So then you further do you or propagate and generate?
Well, you say yeah, exactly. That's right. So the idea is that the carry out is going to be 1 if the generate is true, or if the propagate is true and the carry in is true, right? So that's what those mean. And I don't know if you remember, but I showed this code at the beginning of the semester in the second lecture on System Verilog. This was a module that created a full adder, and I kind of brushed past this when I originally talked about this slide, but you'll notice that in this case, the propagate is XOR, interestingly. I just noticed that. Yeah, it is XOR, right? You see that? And the generate is the and. A and B, propagate is A XOR B. Yeah, so you're right. It is. I guess it is XOR. Yeah, it's XOR. Yeah, I was wrong. It's XOR. A XOR B, propagate, generate is A and B. Yeah, so we got them both in here. But the point of this slide is that notice how P and G are generated alongside S and C out. So it's just a full adder has 4 bits of output now.
I think your way is faster because XOR takes longer.
Yeah.
More delay.
Yeah. Yeah, I don't know. I guess if you used A or B for propagate, I don't know. I don't think that would cause an issue.
And why do we end it with CN?
Oh, in this case, it's a shortcut. Normally the S is A XOR B XOR CN, but in this case they substituted P to reuse P, because I guess the idea is that it's, we're going to reuse this XOR. Right. I think the compiler would have done that anyway, even if you had said A XOR B XOR CN. But
and then down there we and P with CN.
Yeah, as opposed to the normal way you write it. Yeah, it's just a shortcut, optimization. Yes?
So I think I'm understanding what propagate and generate are in broad strokes, but I'm not really understanding how they make this circuit faster.
I'll get to that. Yeah, I'm getting there. Sorry, okay, so the way they make it faster is, the idea is that there's a couple ways you can construct these guys, but the point in this case, the way they do it is they take the adder and they split it into 4-bit chunks, right? So, in fact, you can think of it like, if we go back to the ripple carry, right, so here's the ripple carry. The problem here is we have this long carry chain that goes through, and ultimately the carry chain is a path that starts with C in all the way from the original C in all the way out to C out, right? The goal here is to break that chain. We want to break it. Instead of going from C in to C out, we want to be able to break that chain and shorten the path, right? So the way the carry lookahead adder works is it's going to take each group of 4, and you can set the group size differently, but in this case we're going to take each 4-bit, each 4 columns in the ripple carry adder and put those into a group, right? And then each group will generate a global generate, or I shouldn't say global, but a generate and propagate for that whole group, right? So, because the goal is to figure out, is to be able to calculate this carry in that's in between these two groups of 4 bits. Does that make sense? So that would allow us to basically cut this wire the way it's currently set up as the carry out of bit 3 into the carry in of bit 4. We want to be able to cut that and replace it with another block of logic that'll generate it faster just based on propagates and generates from the lower 4 bits. So the way they have it set up here is that, notice how you've got a little tiny ripple carry adder here that's 4 bits. So this is just a ripple carry adder, right? So the carries inside there are just rippled, right? So the bits, for example, bit 2 here, the 3rd bit from the right, is getting its carry in just from bit 1's carry out, right? But I also take the generates and the propagates from all 4 of those bits, and I combine them together in a way that will give me a global carry out for the whole block. So the way that works is you calculate the generate for the block, which is generate 3 down to 0. So because the block is bits, columns 3 down to 0. So the generate for columns 3 down to 0 is the generate for bit 3, which is the leftmost column. Because if that generate, that's the only generate you need to generate a bit from the whole block of 4 bits, right? Bit 3, column 3, right? Or a propagate from 3 and a generate from 2. Or a propagate from 2 and a generate from 1. Or a propagate from 1 and a generate of 0, right? Now 0 would be the top level carry in on that block. Does that make sense?
Wait a minute, so it returns 4 bits?
No, it only returns, that's a good question. These are both 1 bit each.
Okay.
Right?
It's to generate 4 bits 3 down.
Right, yeah, it uses 4 bit. It uses a set of 4 generates and 4 propagates from the internal generate and propagates within that group of 4 bits. But the ultimate output is 1 bit. So generate 3:0 is a 1 bit output. Make sense?
Oh, and down there, G, I down to J, that's also 1 bit.
Yes, yeah. So this is for bits 3 down to 0, and then this is in general where instead of 3 down to 0, they use I down to J, where I and J can be, for example, 3 down to 0, or 7 down to 4, or 11 down to 8, or 15 down to 12. You know, you can, assuming you have 4-bit groups.
4-bit chunks.
Right. Okay. So what you end up with is, this is the whole schematic for each of those blocks. Inside those blocks there, you have a little ripple carry adder to generate the sums. And then you have this circuit that generates the carry out. And this circuit is a function of the generates and the propagates generated internally, right? But it also has the carry in into the block. Okay, now you might say, wait a second, if that's true, then that carry in, like in order to generate this for that block, I still need that carry in, right? And in order to generate this whole circuit for that block, I need that carry in, right? So the delay of this circuit is still growing linearly with the number of these blocks, with how many blocks I have. But the advantage is that notice this, the path through each of those blocks from its carry-in only has to go through 2 gates, right? And the reason is because of the way the carry out the carry. Oh, sorry, I forgot that actually is not shown here. So the carry out is going to be the generate these guys, generate 3 down to 0, and or the propagate 3 down to 0 and the carry in from the previous block. Okay, so the advantage here is that this carry in only has to go through 2 gate delays from one block to the next, right? Which means that all of this logic is being calculated in parallel, right? Because you might say, well, now that's a long delay, right? Look at this, 1, 2, 3, 4, 5, 6 gate delays there, right? But all of these 6 gate delays in every block are going at the same time. They're in parallel, right? The only sequential part of this is this, which is only 2 gate delays, right? So that's where this thing gets its speed. Speed is through well, it's how any circuit gets its speed, or any computer. It's through parallelism. You're doing all of this workload, well, workload in terms of logic delay, in parallel in each of the blocks at the same time, because they're a function of just the P and G's, which come directly from A and B, not from, you know, upstream in the adder, right? The only upstream connection is this carry in, which only goes through 2 gate delays, right? So when you're calculating the delay of this circuit, the delay is the time required to generate these P and G's, right? And as we just said, what is that? It's 1 gate. It's an XOR gate or an AND gate for P and G, right? From A and B, right? So that's the time for the propagate and generate logic, which is very short because it's, like I said, it's only calculated from A and B. And then you have to add to that the time for the propagate and generate block. So you have to calculate the time to, you have to add the initial time to go through this logic, but only once, because they're all being done in parallel, right? So that doesn't have an n in front of it, right? Or it doesn't have any scaling factor at all. It's just the time for the P and G's from those, from the initial A and B's, then through this logic, which is the propagate generate block, right? But that's, again, that's being done in parallel, so you only count it once, right? And then this is the sequential part, is n divided by k minus 1, which is the number of these you have to go through. And that's going to scale with the number of blocks, right? But it's scaling at n divided by k, where n is the total bits and k is the block size. So if it's a 32-bit adder, you only have to traverse 32 divided by 4, right? So 8, actually 7. Notice there's a minus 1 there. You have to go through 7, right? So from the first input goes through, you're going to go through, well, you're going to go through 7 of these little double gate things, right? 7, right? Because the first one you get as part of that first PG block, right? And then finally, you have to finally add full adders. These full adders, this ripple carry, you have to add the ripple carry delay, right? You might say, wait a second, why aren't this and that in parallel? Well, because of the carry in here, right? So you have to add the ripple carry delay, but it's only k times the ripple carry, because you only ripple carry through this small ripple carry adder inside the block. Yes?
So, I think this is like an approach to divide and conquer, right? Like you have it only ripple carry through a smaller block. But I don't see, the part of this I'm not really comfortable with yet is how the carry bit, like I can understand you take each 4-bit range of a 32-bit number and you add them in parallel and find their P and G and all that. But then how do you recombine them? I can't really understand the diagram.
Well, the way that you recombine them is through another ripple carry, essentially. Okay. Except it happens through, you do all this stuff in basically the first block, right?
Yeah.
So in other words, this delay, is think of that as for the first block, block 0, right? So you have the time to get through this, right? And the time to generate the PNGs, right? Actually, I should do that in another order. Let's start with time to generate the PNGs, right? So that happens first. That gives you these inputs, right?
Okay.
Then you have to go through this, right? Now, just imagine that the first time you go through this in block 0, the carry-in is already provided, so this is free, right? Because that's like the top level carry-in, right? So if you're subtracting, you plug a 1 in there. If you're adding, you plug a 0. It's just hard-coded, right? So you go through the PNGs and you go through this logic, right? And so that takes care of that term and that term, right? Once you get done with that, then you have to go through 7 more of these blocks, but not through the whole block, only through these 2 parts, right? So if I took this whole thing and I replicated it over here for the second block, this carry out would only have to go through this part on the second block, right?
Wait, what's that? I'm sorry.
Because there's an input. We need that input here,
Okay.
right? So this input on the second block, right, would experience a delay, but only like once you generate everything here, you'd only have to go through 1 delay of this to get the carry-in into the next block, which then you would use for that carry-in.
So all of them can do the PNG part in parallel, but then the C part needs to be propagated.
Right.
The C needs to be propagated to the next one in the chain. Okay.
Right. Yes, because the idea is that, yeah, they're doing this part in parallel, they're doing the PNGs in parallel. The only thing that the second block is going to have to wait for is, obviously, it has to wait for all this, yes, but only once, right? It's got to wait for all this stuff one time, because while all this stuff is percolating through here, it's also percolating through the second one over here in parallel. However, I do need to get this through these 2 gates,
Okay.
right? And then over to the second block, and then over to the next block, right? So I have to multiply this delay by 7, which is that n divided by n divided by k, which would be like 32 divided by 4 is 8, minus 1 is 7. So I have to get this through, I have to go 7 more times. After I got through the first one, obviously, I have to experience this delay 7 more times before I percolate that whole thing through.
Thank you.
So,
Okay, and then once I get it through that, and by the way, I think I said that wrong. Well, let me correct something here. After I percolate it, after I pay for this in the second guy, and the third guy, fourth guy, all the way to the 7th one, then I still have to get it into this guy and get it through the ripple carry. That's why this term is last, actually, right? This 4 times the full adder. The reason why this term is last is because you generate 7, you go through, actually in total, 8 of these. You go through in total 8 of these. Oh no, I'm sorry. I take that back. No, 7 in total, because you don't. Well, you do need the glass carryout. So you go through 8 copies of this altogether, right?
Okay.
But after you pay for, I think the first one is folded into this delay. So after you get through the first carryout here, you go through 7 more, right? But even after you go through the last one, after you get the last one, oh, actually, no, I take that back. The last one,
yeah, because that one's already done.
yeah, this one's done. You still have to get this carry in into the leftmost block, right? In order to get into this ripple carry out, or to get the last 4 bits out, right?
And that's why it's 7.
Yeah.
So you're,
Yeah, that part's a little tricky, the reason why they do the -1 here. But it should be easy to see why this T and or, which is just this and or, right,
Yeah.
is scaling not by n, but by n divided by k, right?
Yeah.
Because it's not, you're not doing 32 of these, you're doing basically 8 of these guys, right? Right? And that's the bottleneck. That's the thing that makes this slower as you make a bigger adder. But the time is growing, as a function of n over k as opposed to n as in a ripple carry adder, right? So that's the advantage.
Okay.
so the idea is you're shoving as much of the carry calculation into init time.
Right.
Initialization time.
Yeah, that's right. Yeah, exactly.
I'm sorry. because you did explain it, but what was the last term again? I understand the first three terms.
The last term was this little 4-bit ripple carry adder. So you have to say k, which is 4. Right? In this case, k is 4, n is 32.
Yeah.
Well, actually, I didn't say n could be 64. Whatever, n is the total adder size. But k in this case is 4. Now you can do an 8, you could set k to 8 or 2. There's different ways you can adjust that. But k in this case is 4. And so it's k times the full adder, because when you, in the most significant block, you have to get the carry in, and then you have to then additionally pay for 4 times full adders to propagate, to get it through this part of the circuit, right?
So that's accounting for just the ripple itself.
Right. Yeah. Okay. So that's the equation for calculating that delay. And then finally, the last kind of adder is a prefix adder, and this one's pretty neat. It also has propagate and generates for each bit. But the difference with the prefix adder is, instead of generating one propagate and generate for each for these 4-bit blocks all the time, you can generate an arbitrary propagate and generate for bits I down to j, okay, where the logic looks the same. It's generate plus propagate. It's the generate of the most significant part, right, plus the propagate of the least significant part times the generate of the least significant part, right? Same concept. The difference is that, notice that I have I and j, which are the two ends of the block of bits that I'm doing this for, but I have a third variable called k. And what is k? K is the way that I can arbitrarily divide the two halves of the bits. So I have a range of bits, I down to j, and I split them into two halves. And I can split them however I want. I can say, like, first bit, and then, like, if I have 4 bits, I can divide it between 1 bit and then 3 bits, or 2 bits and then 2 bits, or then 3 bits or in 1 bit. I can divide them out however I want. But k is the least significant part of the generate group. And k minus 1 is the most significant part of the propagate group. You guys with me?
So generated upper propagate as well.
Right. Yeah, so it's always two. So you take a group of bits, split them into 2 groups. You can split them into those 2 groups however you want, but I is the most significant bit of the group. J is the least significant bit. And when I say bit, I mean column. We're talking about columns. This is adder columns. And then K is the way that you split them into the 2 groups. K is the least significant bit of the left group, and k minus 1 is the most significant bit of the right group. Okay? Now you might say, well, what's the point of splitting them at all? Why are we splitting them? Well, this is the part that's kind of interesting. So the way you set this up is, you take your columns, and so first of all, you generate a propagate and a generate for each of the original columns, for each of the original bits, just as we did before. The only difference, there's a difference in notation though. Notice it says a sub I, b sub I, right? So that's 1 bit, 1 column. And then I get propagate I colon I, generate I colon I. Now you might say, well, that seems redundant, right? Why would you just take each number and just say that number colon that number, right? What's the point? Well, they do that for a reason, because they want to generalize these propagates and generates, right? So in the first layer of propagate and generate that comes directly from the input bits is I colon I, propagate I colon I, generate I colon I, okay? And that I is always this, so it's going to be like propagate 31 down to 31, generate 31 down to 31, okay? Then That's the first layer, right? So that's what you get up at the top, right? Then you can take each pair of generate and propagates from the originals, the original guys, and you start to combine them into groups, right? So you have up here 14 and 13. So I've got a propagate and a generate for 14, and I got a propagate and generate for 13. I can combine those with this black box and get a propagate and generate for the range of 14 down to 13 by forming them using these rules, right? Where the rules are what I had. These are the rules. These two rules. Generate is, I've got a k value, right? So the generate is generate I to j of the whole group is generate I to k plus propagate I to k times generate k minus 1 down to j, right? So, and then the propagate of I down to j is just the propagate of the two halves propagated, anded together, right? Because if both halves are both propagate as 1, then the whole thing is propagate 1, right? Okay, so these are the rules that you can apply to these groups that come in. So I take those rules and now I can get generate and propagate for bits 14 down to 13, and also 12 down to 11, and 10 down to 9, right? Make sense? Yes?
And the J, G, I down to K, and those are all 1 bit still, right?
Yes, yeah, they're all 1 bits, but I have I and J and I've got K, right? So when I combine 14 and 13, what is my I and what is my J? Well, my I is 14 and my J is 13. Well, what's K? K is 14, right? So I combine together, I'm trying to get 14 down to 13. So I combine them by setting K to be 14. So I go 14 down to 14 and 13 down to 13. Those are my two halves. I merge them together, right? But then I can continue to create these groupings. So now that I have generate and propagate 14 down to 13 and 12 down to 11, for instance, I can then, now this is where it gets kind of wild, I can combine together another two groups, 14 down to 13 and 12 down to 11. So now I take two 2-bit groups and I put them together. So what I'm getting is, again, I and J is going to be 14 down to 11, so I have a 4-bit group I'm forming. But K is going to be 13, because, so this is I, K, and then J is 11, right? So I take the propagate and generate 14 down to 13 and the group of 12 down to 11, and I combine them together, and that gives me a bigger group, 14 down to 11, right? But then I can also take 13 down to 13, which is a 1-bit group, right? Because there's notice that there's a direct connection here. This 13 drops straight down into this black box. So I take a 1-bit group, 13, that's it, 13 down to 13. So that way my I is 13 and my K is 13, but I can combine that with a 2-bit group, which is 12 down to 11. So I take a 1-bit group that's just 13, and I take another 2-bit group, which is 12 down to 11, and I combine them into a 3-bit group, 13 down to 11. So these aren't powers of 2, because I have a 4-bit group, but here I have a 3-bit group. I have a 4-bit group that I form from two 2-bit groups, and I have a 3-bit group that I form from a 1-bit group and a 1-bit group, which is 13, and a 2-bit group, 12 down to 11. All right, and then I do that, let's see, I've got 4 bits here, 3 bits there. Then I've got 6 down to 3, that's 4 bits. 5 down to 3 is 3 bits, right? Okay, then I have 2 down to -1. What's -1? -1 is the initial carry in. The top carry in, topmost carry in. Okay, so I've got 1 bit at the top, I've got 2-bit groups here, then on this next level I have a combination of 4-bit groups and 3-bit groups, right? Then when I go to the next level, I have 14 down to 7, which is a 8-bit group. But right next to it I have 13 down to 7, which is a 7-bit group, and 12 down to 7, which is a 6-bit group, and 11 down to 7, which is a 5-bit group. Well, how did I form a 5-bit group? Well, because by that level, I now have access to 3-bit groups and 2-bit groups that I can combine to create a 5-bit group. And as long as the combination are together in terms of they're contiguous, right? As long as k, like if k is the least significant group of the upper bit and k minus 1 is the most significant bit of the lower group, I can merge them, right? As long as I have that true, then I can create these groupings that are, again, they're not powers of 2 because this 11 down to 7 is just like an arbitrary, you know, is like a 4-bit, right? And then but over here, I have 6 down to -1, which is a 8-bit group, 5 down to -1, which is a 7-bit group, right? Then I get to the next level, and I have 14 down to -1 because I was able to combine this 8-bit group, which is 14 down to 7, and I can combine it with this 8-bit group 6 down to -1. I merge those two and I get a 14 down to -1. So what you end up with is these groups that go all the way down to -1. This is a 16-bit group, right? This is a 15-bit group, 14-bit group, 13-bit group. But any of the groups that go down to -1, I can use directly as a carry in into that column. Now, I can't do anything with a group that goes, like, for example, this one, 11 down to 7, it's useless. I can't do anything with it except use it to build a better group that gets me all the way down to -1. Once I have that, then I have 11 down to -1, which I can use as a carry in directly into column 12. Right? So all these groups are useless by themselves, but they can be used to build up bigger groups, which eventually will give me a contiguous group down to -1, which will give me my carry-in for that column, for whatever column is I, you know, because again, I down to j. If j is -1, then I is directly usable as the carry-in to column I. Does it make sense? Yes?
This is like the most extreme version of the space is part of the space-time trade-off, right?
I think so. There's other types of adders. I think this is probably this is the fastest one I know of. But people are always trying to come up with faster ways to add or multiply or whatever. This is in the textbook. It's the fastest one.
Mm-hmm. But in exchange, you're using an enormous amount of staged PG prefixes.
Yeah, I don't. You know, it's funny. The textbook calculates the delay for each of these 3 adders, but they don't calculate the number of gates needed. You know, the resources required, right? Which I'm surprised it doesn't.
Yeah.
I'm assuming this uses more resources than the carry lookahead adder. I assume, right? But I don't know that because the book is focusing on the delay. So the delay for this, speaking of which, is the time to generate the initial set of propagate generates, right? The very first layer, right? Which is this. And by the way, going back to your original question once again, the propagate, is it XOR or is it OR? This is showing it as OR now, right? The system Verilog code I showed as an XOR. This never came up. I always just assumed propagate was OR, right? And again, it is OR here, but anyway, propagate and generate, this is when it's II, right? So that you pay for, that TPG. Then you have log base 2 of n times the PG prefix, which is this. Because, you know, 16 bits, and you can see there's four layers, four layers of black boxes. The black boxes are the PG prefix, which is this, right? And then you have an XOR because the XOR is generate I minus 1 down to negative 1. Remember, anything that goes back to negative 1 gets me all the way back to the beginning. That gets me the total, like the final carry in into my column, which is, in this case, column I minus 1. I'm trying to generate a sum for column I, so I need the generate for column I minus 1. By the way, there's a little bit of trickery here because the carry in is just called generate. So when I use a prefix adder, my goal is to just get the generate of I minus 1 down to negative 1. Don't worry about propagate. I don't care, because if I can get the generate all the way down to negative 1, which is the initial carry-in, I don't care about propagate. The generate is my carry-in. So my generate for column I is I minus 1 down to negative 1. That's what I'm trying to get, and then all I need from that is I just have to XOR, it's a carry-in, right? So I just have to XOR that with A and B, and I got my sum, and I'm done adding, right? So this adder scales, the time is scaling as a log base 2 of n. Obviously, you want to scale as a log base 2. It's better than scaling at n divided by k as we did, because the n divided by k for the carry lookahead was still linear, whereas this is scaling up as a logarithmically. So clearly, this is the fastest adder. But again, it's going to be more expensive in terms of gates to set it up. But I don't know how you could build. I don't know of a way to do an adder any faster than this. Yes?
Is a lookup table still slower than this?
Oh, possibly. For smaller ones, probably lookup table would be faster. But the lookup table, the problem with the lookup table is the number of rows is 2 raised to the power of the bits of A and the bits of B, and the carry-in. So if it's a 16-bit, like this adder, you're looking at 32 bits for A and B, plus the initial carry-in, right? So you're talking 33 bits, which is, 8.4 billion rows.
And it has a log base too.
So 8.4 billion, that's like 8.4, billion, right? Gigabytes, right? Giga entries, right?
Yeah.
So that would be too slow. You couldn't do. Now you could do. You might be able to break it into smaller lookup tables and then have to propagate the carry like we did through the. You could, like, for example, you could build a lookup table to replace this ripple carry adder here, right? But then that wouldn't really save you much because you still are scaling. You'd still be scaling as n over k, times the delay of the lookup table. So even if this was a lookup table and you did a linear percolate like a carry lookahead, you'd still have the linear scalability. So I think the prefix adder would be better than, in general, would be better than lookup table based method, unless you had a really small adder.
Or like if you had a lot of memory, would it be better? Like a lot of storage to.
Possibly, but it depends on the latency of the storage. The bigger your memory is, the longer it takes to access it. It's like any memory. Like if you've got papers on your desk, you can get them fast, but you can't fit many. If you put the paper in your filing cabinet, then you got to go look through your filing cabinet. If it's in the library, you got to go. But as you add more capacity, you add access time. That's true in computer memory as well. That's why they have the cache hierarchy.
Even if you abuse associative law, it's still log base 2 of the number of rows.
For what now?
Like even if you do the trick where you do the gate such that every row you divide by 2 every time. Like it's still really slow because I'm not saying this right, but what I'm trying to say is you're right.
Okay.
Sorry.
Yeah, it says here an n-bit carry lookahead adder is generally faster than a ripple carry adder for n divided by 16. But for prefix adder, do they have a rule like that? No. But so here's an example of a question like I might ask. Compare the delay of a 32-bit ripple carry lookahead, and prefix adder, assuming the carry lookahead has 4-bit blocks, because of course we could change that block size. And then the two input gate delay is 100 picoseconds, and a full adder delay is 300 picoseconds. So all you have to do is take those numbers and put them in the equations, and what you end up with in this case is the ripple carry is 9.6 nanoseconds, the carry lookahead is 3.4 nanoseconds, and the prefix adder is 1.2 nanoseconds. And again, it's just a matter of plugging those numbers in. So you've got n, you've got k, t and or would be, this t and or, this term would be 200 because there's, 2 gates, right? Each gate is 100 picoseconds. So this would be 200 picoseconds. And then the full adder, I said, was 300 picoseconds. Okay, so that's the adder. How do you make a subtractor? It's actually easy. You just negate b, and you set the top level carry-in to 1. And why is that? Because that ends up creating a 2's complement of b. If you negate or complement all the bits of b, that'll give you the 1's complement of b, and then you can create the 2's complement by adding 1 to the sum of a in the complemented form of b by using the carry-in, right? So you have to use that top level carry-in, which is generate -1, for example, for the prefix adder, right? That's how you can switch from add mode to subtract mode with an adder. Okay, so how about equality? How do you check to see if a is equal to b? This one, I don't really agree with how the book presented this one. So the book said, you just use an XNOR gate for each pair of bits between A and B, each of the corresponding bit pairs. And then you feed all those XNOR, because obviously XNOR will tell you if 2 bits are equal or not, right? But the problem with this circuit is that then you have to feed in all of those into a gigantic AND gate, which will create a massive AND gate with lots of inputs, which is going to be slow. Right? I wouldn't do it that way. I would do it the way that we did it in this class in your lab, which is to subtract a minus b. Of course, even then you still have to reduce all the bits from the subtraction, down to a single bit, right? So you still kind of have the issue. You have to feed in all the sum bits from having subtracted them into a big OR gate, right? So I guess you can't really get away. But yeah, this is one way to check for equality. Another way is to subtract. How about less than? So we have this one in our ALU as well. So less than is, I don't have a lot of details here. This is for a minus b, and then they check the sign bit of the result. So this is for a signed comparison, right? So if you subtract and you get a negative result, then A must have been less than B, right? What if they were, say, both negative numbers, though? So you have a negative A and a negative B, and you subtract. Well, if A was less than B, you'd still have a negative sum, right? So this works for that as well, right? But what if A is negative and B is positive? Well, if that's the case, you don't even have to subtract, because if any negative number is going to be less than any positive number, right?
And if you subtract a positive number from a negative number, the answer will still be negative.
Yeah, if you have a negative number and you subtract a positive number, yeah, you'll get negative. But you don't know if the magnitude of A was greater than B, though, to begin with, though, right? So this slide actually assumes that the signs of the inputs are equal. So I don't think this works if the signs are not equal. But if the signs are not equal, then it becomes much easier, because then you can just use the sign. So if you look at your ALU design in your CPU, that's the way it works.
Doesn't it still work in that case, though? Because a negative number is less than a positive number. That's true. It's not about magnitude, right? It's just about, like, -1 is less than 0 on the number line.
Yeah, but if you had, oh, that's right, you're right. If you had -1 and -2, and then, yeah, it would be positive when you subtract. Yeah, you're right, yeah. So I guess it does still work. Oh, yeah, you're right, okay, it does still work. Yeah, that's right.
But if you could save time without subtracting, you should.
Yeah, I think, yeah, but then again, all the timing is based on the critical path, so you have to use the slowest, you have to consider the slowest path. Okay, yeah, so that's a good point, thank you. Okay, how about this is a shifter design. So, obviously we use shifter instructions in the RISC-V, and we gave you the shifter code, but how does the actual hardware for a shifter work? Shifters are actually, this is called a barrel shifter. A barrel shifter is a shifter that can shift an input by an arbitrary number of bits, as opposed to just one bit at a time. If it's one bit at a time, that's usually called a shift register. If you can shift by any amount of bits, it's a barrel shifter. I don't know why I don't know where that name came from. I don't understand the name, barrel shifter. But anyway, the problem with barrel shifters are expensive. Some really lightweight processors don't have shifters, don't have barrel shifters. Ours does. But then again, it's funny because the code, the Verilog code for a shifter is very simple, but when you actually generate the hardware and synthesize it, it can still be very expensive. The reason it's expensive is you can see the way it works here is you've got A as the value you want to shift, and the shift amount comes in, and essentially what's happening is we have to be able to take the bits of A and be able to feed those into muxes, where the number of inputs on the mux equals the number of bits that I want to be able to shift. So if I have a 32-bit value I want to shift, I need to have 32 muxes, each of which has 32 inputs. Why? Well, because what the muxes are doing is selecting, basically, you think of it this way. If I have a 4-bit number and I shift it by, in this case, this is only shifting one direction too, by the way. Which way is it shifting? This one is shifting, if the shift amount is 3, then I have 0, 0, 0, and A3. So this is shifting to the right. Because if my shift amount is 3, A3, which is the most significant leftmost bit of A, will end up in Y0, which is the rightmost bit of Y, right? So this is only doing a right shift where the shift amount is specified there. So the idea is that I'm going to take the most significant bit, if you just consider the most significant bit of A, right? That most significant bit is going to be mapped to the most significant bit of Y if the shift amount is 0. If the shift amount is 1, then it's going to come in here and it's going to be shifted to Y2. If the shift amount is 2, Y3 is going to go into Y1, and if the shift amount is 3, Y3 is going to get sent out to Y0, right? Make sense? So for each shift amount, I have to be able to explicitly select each of the outputs as either a 0, which is I'm shifting in 0, shifting in, so this is only a logical shifter too. It's a right shifter, it's a logical shifter, it only shifts in zeros. So I'm either going to shift in, put a 0 out, right? Or I'm going to be shifting a higher significance of A into a lower significance of Y, right? So yeah, if this is a 32-bit, you can 32 to 1 muxes, and that's only for one direction. That's expensive. So shifters can be expensive. Another alternative to that is a shift register, which is where you have flip-flops that are connected in series. So you can take that and you can load something like that in series or in parallel, right? But then once it's loaded, once these registers are loaded, these flip-flops, you can shift just by clocking them. You clock them, and the contents of the shift register moves down by one position each clock. Now you might say, wait a minute, hold on. You're telling me that you're going to connect the output of a register to an input of another register. Wouldn't that violate the hold time? I mean, there's nothing in between. It's a direct. You're going to change the value of Q, and then it's immediately going to go into D, and then you're going to violate the hold time. Yeah, but that's assuming the tools aren't fixing that for you. The synthesizer will make sure it doesn't, because it'll deliberately add buffers in between these guys to make sure that the timing constraints aren't violated. But assuming that hold time is fine, then the shift register will just move data down the shift register bit for bit. In order to fully implement this, though, you got to do some stuff like this. You got to have the shift register has to have muxes in between that allow the value to come from the previous register if the mux is set to 0. Or if you set the mux to 1, you can load it in parallel. You can initialize everything So you see these D0 to Dn minus 1. You can load this guy in parallel by setting this mux, which has a signal called load, to 1. Right? But if load is 0 and you clock it, then the muxes will basically create this serially connected series of registers, which will just move the values down bit for bit, right? So this works as a shifter. It's much cheaper, but the downside is you can only shift 1 bit at a time. Right? Yes. 1 bit per clock.
I didn't really follow the explanation of how it lets the signal move precisely 1 bit over at a time without all of it immediately propagating down the entire wire, like you said.
Well, okay, because that's a good question. That's because each clock, they only take they take a snapshot of their input, right, on the rising clock edge,
Okay.
right? So these guys are set up, these flip-flops only change once per clock.
So they're not latches, they're flip-flops.
Right. Yeah, you have to use flip-flops for this. That's a good point. Yeah, if you use latches, then, yeah, you're right. Then it'll behave like you said. It'll like all spill through, like really fast. It'll create like, yeah. I actually, I've never even tried that. I don't know what would happen if you use latches. But the flip-flops being edge triggered are controlling it. Edge triggered means it's only going to move 1 position at a time because they can only.
It's going to be set equal to the last one at the time of the last snapshot.
Right, and we're assuming that there's propagation delay. So what's going to happen is the rising edge of the clock comes up, right, and it's going to take, there's propagation delay, which is going to delay the update of the previous. It's going to take some time to update it after the clock edge, right? But by the time that happens, you've already sucked in the previous input, right, into the next one down in the next stage.
It's non-zero time to spill through.
Right. Oh yeah,
The
yeah.
clock edge is basically infinitesimal duration.
The clock edge is small. There is the clock edge is a small duration. You still have that aperture time where you have to stabilize everything within the aperture around the clock edge. But the propagation delay of these flip-flops, as well as any additional buffers the tools put in to delay them even more, will ensure that after the clock edge happens, it's going to take some time for the whole thing to update. The clock edge is just the sampling time, is what sucks in the value from the previous slot in the shift register.
But assuming all the flip-flops are the same, that it doesn't matter. If they all have the same time to calculate the output, for the output to change, then we don't even need to worry about.
Yeah, as long as the hold time is, if they update too fast and it violates the hold time, but that's probably, like I said, the tools will ensure that. From the perspective of the kind of the schematic level like this, you can just hook them in, and then you hope that the tools make sure that the timing is okay. Okay. So the shifters, I think we talked about this before. You can use shifters as multipliers and dividers as long as the value you're dividing or multiplying is a power of 2. So left shift multiplies by a power of 2, by a power of 2 where the power is the number of bits you're shifting. And if you shift to the right, you're dividing by a power of 2 where the power of 2 is the number of bits you're shifting right. Okay? So what happens when you don't want to multiply by a power of 2? How do you do that? You have to, I think I had a question on a quiz or exam that kind of led into this a little bit. If you don't want to multiply by a power of 2, you have to basically add up a combination of shifted versions of your value, right? So the value, so when you multiply, you have a multiplicand and a multiplier, and you can actually, it doesn't matter which number you put in as the multiplicand and the multiplier, because multiplication is commutative, right? But the multiplicand, the reason why we give them labels is because the multiplicand is the value that we're shifting. And the multiplier is used as a bit mask that basically defines how many of those shifted versions and by how many we want to add up, right? So basically a multiplier is a shifter and an adder. You take the multiplicand and you shift it by the number of bits corresponding to each of the 1 bits in the multiplier, and then you add them up. So as long as you can shift left and add, you can build a multiplier. That's all you need to do. So the way that you can think of this is like a grade school multiplication, where you take your multiplicand and multiplier and you start with the digits of your multiplier starting on the right. And for each one of those that's a 1, you put a copy of the multiplicand there, right? But you also shift the multiplicand over by whatever digit you're looking at in the multiplier, right? So in this case, I'm multiplying 5 times 7, so I take 5 shifted by 0, and I add 5 shifted by 1 because that 7 has a 1 bit in bit position 1. And 5 shifted by 2 because there's a 1 in bit position 2 in the multiplier. And then I don't add the multiplier shifted by 3 because bit 3 in the multiplier is 0, right? So basically I take 5 plus 10, because 5 shifted by 1 is 10, plus 20. 5 plus 10 plus 20. Is that right? 5 plus 10, right? And then this next one is 5 times 4, right, is 20, right? So that's 1, 0, 1, and then 1, 1, right? And it's 35, which is 5 times 7, right? So it works out, right? So basically that's all it is shifting and adding. It's pretty simple, right? So how do you build it in hardware? Well, that's where it gets a little more complicated than you might think. So, so there's 2 versions of the multiplier circuit shown here. The one, and this confuses me sometimes. So the circuit in the middle of the slide here is showing the multiplier built with full adders, single bit adders. Okay, so keep that in mind. Each of these little each of these symbols in here that look like a V is a single bit multiplier. Okay, so keep that in mind. Okay, then I've got A, bits 3 down to 0 is my multiplicand, and B is my multiplier. So what I'm doing with the multiplier is I'm ANDing each bit of the multiplicand by a bit in the multiplier. Does that make sense? Why am I doing that? Because I want to be able to turn on or turn off the multiplicand depending on the corresponding bit in the multiplier. Does that make sense? So for example, in this diagram, I've got the first level, I've got A 3 down to 0, and B0 is the first bit of the multiplier, and B0 is connected into these AND gates, which is turning on or off each bit of A0 into the, now this is where it gets weird, into the right input of each of those adders, right? So if you look at the top layer of adders, there's a left and a right. There's 2 operands. The right operand is being fed by an AND gate, which has also got bit 0 of the multiplier. So bit 0 of the multiplier comes over here, and it goes down into this guy, this guy, this guy, and to this other one that's just an AND gate. Make sense? Okay? Then if you look at the left input, it works the same way, except the left input uses B1 for the AND gates, right? So in other words, there's a left and a right input to the adders. The right input uses B0, ANDs with B0. The left input ANDs with B1. Make sense? Okay? Now, how does the shifting part work? Where is it shifting? Well, the shifting, that's where it gets kind of weird. The shifting is, you'll see that the bit 0 of the product is coming just out of an AND gate. It's not being added to anything, right? But if you go to the first full adder from the right, you can see that it has 2 inputs, but the inputs are shifted relative to one another, because if you look at the first input, it's I'm adding A0 combined with B1, and the second input, let's see, where's the second input coming from? The second input has B0 ANDed with what are we adding with here? A0 goes into one input, and the second input is A1. Yeah, the second input is A1, right? So basically, I'm adding A0 to A1, right? So I'm adding two different bits of the A input. So that's how the shifting is done. Does that make sense? Right? So I'm taking A1 and I'm adding it to itself, but I'm adding it to different bits of itself, right? One bit off, but each of those bits is gated by a different B bit, multiplier bit. Okay, all right, well, I'm out of time for this. I'll finish this on Monday, and I'll probably talk just a little bit about CMOS design, and then we'll go through a quick review for the exam. If you have any questions about any of the quizzes, you can. I'll give you some time to ask about those on Monday. Monday will be our last class, and so everyone have a happy Thanksgiving. And we'll see you next week.